Okay. Okay, that's better. Yeah. So with a random forest, you also resample your features. So you don't necessarily use all your features at every node to um, to split your nodes.
In
So
fact, you definitely don't use all the
that's a
features.
difference, right? So that's your difference. That's a difference.
Okay. And there was one other thing, one of the slides, Professor, when we were traversing the tree, in one of your slides, we were comparing the value of x2 greater than, like for some of the decision nodes, for some of the branching nodes. But at the bottom, we were comparing x1 values, right? So I just wanted to understand the behavior, like for the top half of the tree, we were comparing values of x2, and then at the bottom half of the tree, we were comparing x1.
No, that's not. I mean, you can sort of alternate
Yeah.
between. I mean, it depends on the how the splits are computed. I mean, when you compute the which split gives you the best Gini index. So that can be, so you can split at x1, and then next time you split at x2, and then you split at x5 or whatever. I mean, that can be that sort of depends on the data.
So whichever reduces the impurity.
Yeah, exactly. Which whatever reduces the impurity the most.
I'm going to see if I
there's
can find
no
something.
there's no there's no sort of set way of that you first do all the x1s and then the x2s and stuff. That's not the case. Okay.
Yep. Yeah. Thank you.
All right. Okay. So let's.
I have one question here.
Yeah. Okay.
Yeah. So in the bagging example, right, or in the tree example, if when Adam was doing it on Boston data, right? So the tree is dividing the data itself into more homogeneous kind of data, right?
Yeah. Right.
And then running regression in that cluster using all 13 features, right? And that's how it tried to make the data more and more homogeneous so that the fit is better in those small subsections. So that was being done, correct?
No regression.
No,
No.
in Boston example.
In the Boston example, which was numerical, it's called a regression tree. But what you're doing is, instead of using entropy to, or accuracy to split, you're using what's really the variance or the mean square error that you get. And the basic fact is, when you take the maximal split, you're going to wind up with two sets of data for which the total sum of errors in each one is smaller. The sum of them is smaller than the parent node.
Yeah, I mean, the function you get from a regression tree, it'll still be a piecewise constant function. I mean, you can only take finitely many values, so it's not like you're getting a line or something else.
Let me share my screen. I want to show something. May help.
Because I'm just wondering that mean square error will come from y and y hat, right? And y hat comes from a model. So there has to be some model in each cluster so that we can say that mean square error has reduced.
Yeah, but the y's are going to be the averages of. So if you have a split and you have the y's in each subset, then it's going to be the mean of the y's minus, and so it's going to be the sum of the mean of the y's minus yj squared, sum of the y.
Here, I'm gonna.
So deviation of the y's.
Here, you're now seeing my screen. So this is I think actually from the Boston data, and this is a tree that actually happens. So the first split is on this LSTAT being less than 9.715. That splitting the data into the ones the data points which LSTAT is less than 0.9715 and bigger than 0.9715 creates the maximum decrease in mean square error. So above here, you really had all your data. And you have the variance, which is just the total variance of the data set. After the split, you now have two data sets. And the point is the variance of this one plus the variance of this one is less than the variance of the entire data set. And in fact, the split is such that there's no other split in the data. There's no other choice of the variables, no other choice of values, which will decrease the sum of the two variances by as much as that split. That's what the algorithm, the tree algorithm does, right? So now you have this data set, which doesn't look like this data set at all. It has one important distinction, the LSTAT. On this data set, it then finds that if you resplit again by LSTAT, you get the maximum decrease in the mean square error of variance, right? On the other one, where the LSTAT is smaller, now you split on something completely different. But what's happening is if you look at the variance of this data set, you now have four data sets, 1, 2, 3, 4. And what's true is the sum of the variance of this data set plus the variance of this data set is maximally less than the variance of this data set. And the variance of this data set plus the variance of this data set is maximally less than the variance of this data set. Now, what happens when you get to these bottoms, when you get to the, the leaves? You then predict, for anything that fits into this category, the average value or the mean of all the data points in that set. So if you ran something new down the tree and it had LSTAT less than 9.175, but rooms were greater than 7.437, you would predict 46.38 or $4,638 for the value of that house. That 46.38, which remember is thousands of dollars, is the actual mean value of all the elements of the Boston data set that have LSTAT less than 9.175 and rooms greater than 7.437. So it's called a regression tree because in the end you're getting a numerical value, right? And because you're using a mean square error, which is the usual, loss function for regression, to calculate this reduction in our noise, if you will. But there is no actual regression. No regressions were harmed in the making of this tree.
Right. Yeah. So you're not getting a line or sort of, you're just getting a function that's piecewise linear or piecewise constant. So the only values that this function you get from the tree can take are those you see at the end of the leaves here.
So for example, with this tree, there's 1, 2, 3, 4, 5, 6, 7, 8, 9 values. And so if you think of this space, and I don't remember how many variables there are. I think there were 13 maybe in the Boston.
Well, I mean, it has to be a power of 2, so there must be 8.
Well, maybe I'm missing something. But you could have duplicated or
4, 5, 6, 7, 8. There are eight leaves, right?
It doesn't have to be power 2 because you could have different number of splits on different trees, but it has to be even, that's for sure. But so all it's doing is it's separating the speed. If you stopped here, you would have the function that took the value, I don't know what, but it would take some value. If LSTAT was less than 9, it would just literally split it in 2. It would just take 2 values. Now what happens is on here, it then takes that half a space and splits it in 2, right? But again, on that whole, it's piece, as Neil said, it's piecewise linear. But the picture is kind of, to my taste, a little different when you have more than 2 variables. But it is piecewise linear. It's just
piecewise constant.
Spaces.
Constant.
Yeah, it's piecewise constant. It's just going to take, how many values did we count here? 1, 2, 3, 4. Well, let's see, 1, 2, 3, 4, 5, 6, 7, 8. It's just going to take 8 values. It's there's only 8 choices for what it'll guess in this particular tree.
Right.
So in bagging, it creates multiple such trees, and the final value is the mean value from each of those trees, right?
Right.
Yeah. From each of those, yeah. From each of those data sets. So it splits it here. It splits the data set into 8, and the value for each of those is the mean of the y values of each of them. Well, I'll be talking about that hopefully if I can.
And just one last question, quick question. In random,
I'm going to stop sharing.
In random forest, it's possible that you pick let's say you're picking 4 features at a time, right? Randomly. If you pick 4 features which are no predictivity, no forecasting power, still it ends up in giving good prediction because there are so many trees. Is that the reason? Because some of those trees may comprise of those predictors which do not have any correlation with the predict variable.
I don't know. I don't know.
I mean, you'd have to posit that, you know, if you created a random forest where all the variables really had nothing to do with the data, right? And it's theoretically possible that, you know, you could create a tree or even an ensemble of trees that did well, but it's comparable, you know, to the monkeys typing Shakespeare kind of a thing. It's theoretically possible that a monkey will type Shakespeare. The smart money says it isn't going to happen. And, you know, if the bottom line is we're talking statistics. With statistics, you cannot have deterministic assurance, no matter how good it is. And that's always going to be the case. You know, when you do create statistical models, there's always the chance that you just got incredibly unlucky. You got incredibly unlucky on your training, and you got incredibly unlucky on your test. And you just have garbage. And all it's going to take is the first time you go out in the real world and it'll fail. Or worse yet, it'll succeed the first time you go out in the real world. And the second and third time, it'll just fail miserably. You know, anything, you know, it's the old quote from Ecclesiastes. The race doesn't always go to the swiftest nor the fight to the strongest, but that's the way to bet it. So that's not an exact quote from Ecclesiastes, but that's the gist of it. And the same thing has to be true, you know, in any statistical model.
Yeah, you have to select your data with some care. It's not. I mean, it's like, again, if you try to predict the S&P 500 from the price of butter in Bangladesh, you might get a very high correlation, but it doesn't mean it's going to predict very well. So there are all kinds of spurious things that can happen. Okay, but should we get started? So
yes,
because I have a lot of stuff here. So. Okay, I will then start to share my screen.